Clark came to see me earlier this morning. His air conditioning went out completely last night, and his house was burning up, and he had to go meet with the guy today, so he won't be here today. So let's pick up from, so let's start there. Oh, I've already started the recording, but let me mark it here. Turn to the page and didn't mark. Catherine's here. Okay, today's the 29th, tomorrow's the 30th, then we're into May 1st and 2nd. Okay, I've got you marked. Okay. All right, we'll start from this slide. And before we get started today, let me make this major request. Have you done the student course evaluation yet? Okay, please do those. You don't have to do it right now, but please do it. Just wanted to make sure to remind everybody to do that. So I saw Clark, I forgot to say it to him, but I'll try to catch him later. I think I said it last time too. Okay, now what we're going to do today, I'm going to try to spend about half of our time on partial differentiation, and then the second half of the time on multiple integration. Those are two big topics that we need to hit in Cal 3 that we didn't get a chance to. There are some others that probably are worthy of being hit, but these are all we're going to be able to handle today. So this is Chapter 13 still. Well, actually, this is our first introduction in Chapter 13. We're starting in 13.3, partial derivatives. The first two sections were the theory leading up to it. We're going to do it here. And our objectives here is to find and use partial derivatives of a function of two variables, two or more variables. Well, no, the second one, find and use partial derivatives of a function of three or more variables, and then find higher order partial derivatives of a function of two or three variables. Okay? More than one. Yeah. So let's get what we can. So what do we mean by partial derivatives of a function of two variables? You can determine the rate of change of a function f with respect to one of several of its independent variables. Let's say this probably is a really dumb example, but say rolling a bowling ball across the floor here. And what I wanted to track would be the position of a point on the outside of that ball, and however it was going to do. That's going to be a function of the x component, the y component, and the z component, because however it's turning with regard to that axis, that's going to mark that. But it's also going at a certain speed, so it's got position on the floor as a function of time. So the function of x, y, and z would be doing this as it's rolling this way, so who knows what that would look like. It would be awful. But you see there are four independent variables in regard to that, okay? And to any one of its several independent variables. This process is called partial differentiation. The result is referred to as a partial derivative of f with respect to one of those chosen variables. We can only take a derivative with respect to one variable at a time, but then you can do multiple variables. Okay? And here's the definition. Definition of partial derivative of a function of two variables. If you have z, your dependent variable here, is some function of x and y which are both independent of each other. Doesn't matter what x is doing, y is doing whatever it wants to, and y, what it's doing doesn't matter to x, but z depends on both of them. So you have one dependent variable, two independent variables. Then the first partial derivative of f with respect to x and y are the functions, and there's a couple of different ways to express these. Here's one. We're going to have another one a little bit later. F sub x. The partial derivative of f with respect to x. Okay? And this is f sub y, partial derivative of f with respect to y. And here's what it's defined as. Partial of f with respect to x is a function of both x and y. It's the limit as the delta x approaching 0, of f of x plus delta xy minus f of xy. Notice we don't let the y change. It's not changing. It stays y. X changes. It goes from x to x plus delta x. And that's what we're dividing by there. So that's the partial with respect to x. Partial with respect to y, partial with this function f with respect to y, but f is a function of both x and y. If the limit is delta y approaches 0 of f of x, comma, y plus delta y minus f of x, comma, y. And here, the x isn't changing any. The y, though, is changing from y to y plus delta y. And then you divide that, and that gives you the limit there. Okay? Provided these limits exist. Of course, if they don't exist, then all bets are off. But it's just like our regular derivatives, only we're only doing one at a time, even though we've got two variables that are dependent. This definition indicates that z, which is a function of x and y, that if z, a function of x and y, this is not a good sentence here. This definition indicates that if z, which is f of x plus y, there's something missing there. No, I guess that's it. Okay. This definition indicates that if z is equal to f of x plus y, then to find f sub x, you consider y a constant. Like I said, it's not changing, so just count it as constant. Differentiate only with respect to x, and similar to find partial of f with respect to y, treat x as if it's a constant, and differentiate only with respect to y. That's the key. Treat the other variable or variables as if they're constants, and only differentiate with respect to the one in question. So here it says to find f sub x for f of x, y equal, 3x plus x squared, y squared, plus 2x cubed, y. Let's find f sub x. Okay. Let me get my pen back. F sub x would then be what? Do it term by term. Partial of 3x with respect to x. Derivative of 3x. 3, okay? That's it for that one. Minus, do this term. What's the partial with respect to x only of x squared, y squared? 2x, y squared. Treat the y squared as if it's constant, just like if there had been a 3 in front of that. That would have been 2 times 3. Well, y squared is just a constant. So treat it as a constant, leave it alone. 2x, y squared. Don't derive it, just leave it, just whatever it was. Okay, next. 6x squared, y. Perfect. Consider y to be a constant, differentiate with respect to x. Okay? Let's go on and do the other. Let's do f sub y. They don't ask us to, but let's do it. Yeah, let's do it with that top one. All right, okay. Now, if it's a constant alone, derivative of that is 0. If it's a coefficient, like it was here and here, then you carry the coefficient. Okay? Here, that's just a constant. Derivative of a constant is 0. Okay? Minus. Yeah, we're doing with respect to y now. Treat x as if they're constant. Okay, and that would be like it was a coefficient. 17 or whatever it was, you know. That would be 2x squared y. Yeah. Treat the x squared as if they're a constant, but you have the variable y in there, so 2 times whatever that constant is, x squared, times y. You reduce that by 1. Okay? Plus 2x cubed. Stop there, because that's derivative of y is 1. So whatever its coefficient is, that's all it is. So there's your f sub y. Very good. Okay. Well, the problem didn't ask you to, but they went on and did the same thing we did. So the first one is 3 minus 2x y squared plus 6x squared y, and f sub y was minus 2x squared y plus 2x cubed. Perfect. Okay? Let's see how they did it. I think it's the same way we did. So f sub, yep, just like what we did. Okay? To find f sub y, consider x to be a constant, differentiate with respect to y. And there you have that. Oh, they wrote their problem in 2 sections, but did the analysis in between those sections. So that's what we got, too. Okay? Now, time out here. There's nothing wrong with leaving it just like this, but sometimes they'll get a wild hair and just decide, well, let's group terms, you know. So you could have factored out the 2x squared for both terms and had a minus, well, let's factor out the minus 2. Minus 2x squared times y, and if you factor out the minus with that, then this becomes a minus x. Okay? So you'll sometimes see them do that. So this would have wound up y minus 2x squared times y minus x. Which in some ways is a little simpler way to write it, but they didn't bother doing that. But no, they can do that. Okay, let's look at the B one. For xy, I think they left out the function, didn't they? Yeah. This is supposed to be for f of xy equal to log x sine x squared y. Good deal. We just doubled the class size. Okay, this is here. Okay, we're doing partial derivatives. It's something that we needed to do in the course. We just ran out of time, so I'm just doing a quick course on it today. Okay? And the general rule is when you have a function of more than one variable, meaning more than one independent variables, x and y being independent, then you, if you're doing the partial with respect to x, and it's one way to express this is f sub x, means the partial derivative of f with respect to the variable x. Okay? That means you take the derivative of this, whatever this is, with respect to x, treating the y as if it's a constant. Then when we turn around and do the partial of alpha with respect to y, we'll treat x as if it's a constant and take the derivative only with respect to y. Okay? So, if we're trying to find f sub x, okay, what would that be then? What kind of rule do you have to call into play here? The product rule. This is a product of two expressions, two functions, right? So, how does the product rule go? Okay, it's uv prime plus vu prime, right, the derivatives. So which one you want to start with? Log x or sine? Which one are you going to start with to take the derivative of? You want the it's the first times the derivative of the second plus the second times the derivative of the first, or the second times the derivative of the first times the first times the derivative of the second. It doesn't matter, but it's a sum, you know. Which one you want to start with? Do the derivative of the sign or leave the sign constant? Not constant. So I got derivative. So we'll write down the first one, log x, and then take the derivative of this with respect to x. And what would that be? Derivative of sine is? Yes, cosine of same argument, x squared y. Now the chain rule part of that second part is take the derivative of x squared y with respect to x only, though. No, you don't do a cosine again. You've already done that. Just the chain rule is the argument, yeah. Times 2xy. Treat the y as if it's a constant. So it's just like a coefficient of that. Like it was yx squared, where y is just some coefficient, 17 or something like that. Then the derivative of that with respect to x would be 2 times 17, or whatever y was, times x. So that's the first part of the product rule. The first times the derivative of the second with respect to x, then it's plus, what's the second part? Derivative of the first, and what's the derivative of log x? One over x. Derivative of log x is 1 over x. Okay? Times the second one. Well, the second one is just this. Sine of x squared y. Okay. That's your partial of f with respect to x. Now let's do partial of f with respect to y. Well, except that you see the log x is not a function of y. This one, both this part and that part are functions of x. This one, that's not a function of y. So we don't have to do anything to that, because if you did treat it, derivative of a constant is 0. So basically you treat this like the coefficient of sine, like 7 sine x squared. Okay? It's just a number there. It's just log x. So that's exactly what we do. We just write down the coefficient, log x, and what's the derivative of sine x squared with respect to y? Cosine x squared y times just the x squared part, because you're taking it with respect to y, so that's just this to the first power, so it'd just be x squared. Okay? Now, we can write them in different orders if you wanted to. Probably I would write the x squared in front. X squared log x times the cosine of x squared y. I don't know if the book has any preference there. Let's see what they did. Well, we'll see in a minute. Well, let's just look and see now. The first one was log x cosine x squared y times 2xy plus 1 over x, or they've just put sine x squared y over x. And the second one, they said, they wrote it separately. They wrote it just like we did. Log x times cosine x squared y times x squared. They wrote it like we did the first time, not like how we wrote it. Okay, does that make sense? Let's see what they did. Sorry about this time. Every day, the old head starts clogging up, and I don't know why. I ate lunch, I drank plenty of fluids, I did everything normally, and it was still, this time after lunch, it just, okay. So here's what they did. They did the first times the root of the second. Derivative of the second, the first part of it, the outermost function is sine, derivative of sine is cosine of the whole thing, x squared y. Cosine of x squared y. Then you do the chain rule, derivative of the inner part, which is just 2xy. Okay? So that's the first times the derivative of the second. The second had a what do you call it? Goodness gracious. Composite function. Composite function of sine and that stuff. Okay? So you did derivative, you did the chain rule, derivative of this, the outer part times the derivative of the inner part. Then you did plus the derivative of the first, which is 1 over x, times the second part, so you just write that over x. That's the partial derivative with respect to x. Okay? The part with respect to y, you find f of y, f sub y for the same thing. And you'll find me saying f of y when I mean to say f sub y. Okay, that's what f sub y. Partial of f with respect to y. Consider x to be constant, differentiate only with respect to y. This just becomes a constant, a coefficient out front, just a constant. And this part is just a constant. So you're doing a constant times the sine of a constant times y, okay? So that derivative would be this coefficient, log x, times derivative of this, which is cosine of x squared y, times derivative of this with respect to y, and that would just be x squared. And that's how they leave it. Now, I don't mean to bias you or anything, but the reason I don't like leaving it like this, especially if you didn't put that outer set of parentheses here, someone might confuse and think you're taking the cosine of x squared y x squared, and you're not. That's a separate function, so that's why you like to put it out in front, so it's not at all ambiguous what the argument of cosine is. All right. So here's the notation, another way to express this. For z is equal to f of xy, the partial derivatives f sub x and f sub y can also be denoted by, and these are almost Leibniz type notations, except when it's a partial, you don't write a d by dx, you write this little symbol. It looks like a crooked little d, okay? And I don't even know if they have a name for it. I just call it partial with respect to x. That's the partial notation. The partial with respect to x of f of xy. And that definition is the partial of f with respect to whatever this lower variable is. And that's why you subscript that. Partial of f with respect to x of f of xy. Another way you can write it, since this is your z, it's z sub x. So f sub x or z sub x, all the same. Or partial of z with respect to x, and partial of this with respect to that. Partial, if it's a crooked one, derivative, this is a straight one. Okay? And this is partial with respect to y of f of xy, which is partial with respect to y of f of xy. Or z sub y, partial of z with respect to y, which is also partial of z with respect to y. Okay? Partial derivative with respect to y. The first partials evaluated at a point AB are denoted by, you draw a vertical line there and put at AB. All right. Brian. Okay. And by the way, there's a picture in your text of Jean Laurent D'Alembert. I guess that's how you say it, something like that. The introduction of partial derivatives followed Newton's and Leibniz's work in calculus by several years. Between 1730 and 1760, Leonard Euler and Jean Laurent D'Alembert separately published several papers on dynamics in which they established much of the theory of partial derivatives. Those papers were used functions of two or more variables to study problems involving equilibrium, fluid motion, vibrating strings. Can I get again what your majors are? Kimmy? Emmy? Okay. Wouldn't be at all surprised when it mentions here vibrating strings, equilibrium. Yeah. Which?
Construction engineering.
Construction engineering. Equilibrium again. Building vibrates too, so it's not strings but vibration. That would be it. And you are? Second?
Education.
Oh, education. Wow, way to go to take Cal 3 for education. That's incredible. Math education particularly? Fantastic. I'm proud of you. Okay, way to go. So you'll just need to teach it. So that's all. Whether you ever get classes, college or high school. You may have some advanced, what do they call it, AP classes that would get into this, but that's about all I would think. Okay, but anyway, these are your partial derivatives. How you do them. Just like derivatives, lots of different ways to denote them, in the notation. So if you're evaluating at a point, put the vertical line AB here, and then you denote that as Z sub X at AB, L sub X at AB, partial of Z with respect to, lots of different ways to do this. Or the partial of Z with respect to Y, but evaluated at the point AB. That would be the partial of F with respect to Y at AB. Partial Z sub Y at AB, partial of F with respect to Y at AB. Lots of different ways to write those. Okay. The partial derivatives of a function of two variables, f of x and y, have a useful geometric interpretation. So let's say this sheet here represents z. Z is this red strip here. Looks like it's coming from a point back here and going up like a cape or something like that. I don't know what it is. Some shape here. Well, the partial with respect to the partial of f with respect to x. This is a function f. F is a function of x and y. You have to give an x value and y value up here, and that gives you your z value or your partial or your function as a function of x and y. Okay? So the partial of f with respect to x at this point, x1, y1, z1, or x0, y0, z0, whatever you want to name it, at this point down here, the partial with respect to x, let's see. If y is equal to y0, well, there's the plane where y is equal to y0. You come out positive on the y plane until you reach the point where it intersects the y-axis at y0. This is the plane y is equal to y0. No x dependent. It's parallel to the xz plane back here. Completely parallel. It's where y is constant, y is equal to y0. Okay, if y is equal to y0, then z here is a function of x and y0, because y0 is fixed now on that plane. Okay, so if you're fixed at y0, in other words, you're holding y as a constant at y0, then the partial of f with respect, partial of z with respect to x, and partial of f with respect to x would be the derivative of that curve cut by that plane on your surface z, which is f of x, y. Okay? Where this plane, y is equal to y0, cuts there, this would be it. And if the point here was x0, y0, and you go up here to find z0, then it's that tangent line right there. Okay? And the slope of that would be the partial of that with respect to x. So if you're holding y constant, literally you're holding it constant. You're cutting it right there and then taking the derivative of that curve that's made by this plane and that function up there. That would be your partial of alpha with respect to x, with y being held constant. Where? At y0. If it was at 0, it would be the curve back here. If it was at y0 minus y0 divided by 2, that would be right here, then it would be that curve. Oh, getting a decent class today. Could it be the day they've been dreading all term? The last day of class? Oh, no. Okay. So, we're taking partials with respect to, you got partial derivatives. Okay? And this is a geometric interpretation of that. If you're holding one constant, this example is y constant, then you're taking the partial with respect to x. Okay? That would be the plane where y is constant, except for y is equal to y0 here, and then the derivative of that curve right there. Slope of that curve. Okay. Therefore, alpha sub x, the partial of alpha with respect to x, at the point x0, y0, is the limit as delta x is approaching 0 of alpha x plus delta x0 plus delta x y0 minus alpha x0 y0. So the y's are held constant at y0. The x's are allowed to change from x0 to x to x0, from x0 to x0 plus x, taking derivative at limit in fact approaching 0. That represents the slope of that curve at the point x0, y0, and then alpha of x0, y0, which they earlier called z0. This is exactly what that would be. Notice that both the curve and the tangent line lie in the plane of y is equal to y0. It's got to be. Okay? And the curve and the tangent line to the curve are in that plane. All right. Similarly, the partial of alpha with respect to at x0, with respect to y at x0, y0, do the plane at x0. Wherever that is, come out here at x0 units. And then here's the curve, because that's coming from that direction. That's indeed your intersection of x equal to x0 and the remaining part of that function. That would be slope of the tangent like that. Okay? The point here would be again x0, y0, alpha of x0, which is they show as z0 here. Okay. And then at that point, the slope of the tangent line, actually, this would be going this way, because you see you're going increasing y, so the slope would be like that. That would be a negative slope. Okay. The earlier one was a positive slope. No, wait. Let me think on that. No, the following was a negative slope too, because you're going from x equals 0 to this way. So again, that's a downward slope. So both of those would have been negative slopes, just because of the orientation of that sheet at that point, those points. Okay. I guess that's all we need to do on that. All right. Informally, the values of partial of alpha with respect to x and partial of y with respect to x at some point, x0, y0, z0, denote the slopes of the surface in the x and y directions respectively. This is the slope of alpha with respect to x at that point. Whatever that point is in space, what's the slope of the function with respect to, that's the x-axis, with respect to that x-axis. And what would be its slope with respect to y, something in that direction. Okay? So here's example 3. Now, did we skip to somewhere? I think we did. So let's do 2. We'll do 2 right here. For f of xy equal to x e to the x squared y find f sub x, and then we'll find f sub y. Okay. And evaluate each at the point 1 log 2. Goodness gracious, that writing's terrible. But at least things are running better this morning. This morning, if I touch the computer anywhere, the light will go off. The projection will go off. All I figure, when I checked it after that class, I could tighten the thumb screws on this input to the computer from the projector. I could tighten them maybe an 1/8 or a 1/16 of a term, and now it's working fine. So evidently there was something in there that's not quite making its connection right. And if I even touched the computer, it would go off. Certainly the screen, if I touched that, it was just wacko. All right, so let's find f sub x. How do we do this? What rule is required here? Take the partial with respect to x. Anybody? Second? Chain rule, that's certainly going to be used, but before that, the product rule. Okay, is that what you said? Yeah. Yeah, because you have a product of 2 functions first, and then when you get to this function, you're going to use a chain rule. So yeah, there will be chain rule, but we first do the product rule. So how does the product rule go? We're taking with respect to x. Of what? Of the x? Is that what you said? So you want derivative of x first. Okay, what's the derivative of x? 1 times the second function, e to the x squared y. Okay? So there's the first part. Derivative of the first times the second, plus x times e to the x. Okay. I'm sorry. Plus e to the x squared y. Sorry, I can't hear. Okay. Is that what you said?
No, it's 2. You gotta multiply by 2x.
Right, okay. That's what, yeah. At some point you need it to. So multiply this by 2x then, and that's what you get. Okay. Now, I just was trying to hear which way you were saying. How I usually do it is first x times derivative of this. I usually write this down, e to the x squared y, and then multiply by its derivative, which is another 2x, but we left off the y. There is a y there too, because you treat the constant, the function, the variable you're not using as if it's a constant. So this is like it's a coefficient of this. 7x squared. You know. So you do have this y included. So it's so many moving parts here. The first, you did the easy one, the derivative of the first times the second. Done. Plus the first, and that's where the 1x comes from, times the derivative of the second. The derivative of the second is e to the x squared y, then times the derivative of this with respect to x, and that would be 2 x, y. So you need to multiply this x you have here by 2, another x, making x squared, then y. So that's it for that. Okay? Let's do the same for f sub y. What would you use here? Okay, you don't really need the product rule here because this is not a function of y.
Let's say chain rule.
Oh, chain rule. Okay, I'm sorry. I can't hear. I can't hear. Okay. So it's only the chain rule. So how would that go?
It'll be x, y.
X e to the x squared y. Now do the chain rule part. What would that be? Yeah. No. With derivative with respect to y, which would be another x squared. So that makes it x cubed. Right? Yeah. This one you keep the x's, treat the x's as if they're constants. Okay? So x squared would be a constant. Okay? So that's what it would turn out to be. All right? Now let's go back and evaluate each of these at the values x equal 1, y is equal to log 2. Okay? So here's f sub x at 1 log 2. Okay? And what would that be? I'll just get it started. E to the x is equal to 1. So x squared would be 1. So that would be 1. The first part's 1. And times the y is log 2. E to the log 2. Okay? Because the x is 1 here and x squared is 1 here. So the y is just log 2. So it would be 1 times log 2, which is log 2. Okay, there's the first term. Plus 2 times 1 squared is 1. Y is log 2. Then you have e to the 1 times log 2. Goodness, I can't write log. This morning I did that too. It just was not right. Okay? Okay. I did it again. Yuck. Okay. Get it again. Well, I think part of it's the pen is not picking up well. Okay. Log 2. Okay. All right. Let's simplify that a little bit. What is e to the log 2? 2, exactly. Plus, okay, 2 log 2 doesn't change, and e log 2 would be 2 again, so that would be 2 times 2, which is 4 log 2. All right, there's that evaluated there. Let's do our f sub y evaluated at 1 log 2. Eyes are just stinging. Well, 1 cubed is still 1. E to the 1 squared is e to the 1 times log 2, so that would just be e to the log 2, which again you said was 2. All right. The first one. Oh, sorry. First one. Yuck. Okay, there it is. I finally found it. Okay, right. They wrote the first one, they wrote in reverse order to what I did. And they split it up differently. But they have a 2 there, and x times the x is there, is our x squared. And they have a y there, And so it's just 2x squared y, which what we got, e to the root 2, which is, oh, there it is. Okay, I lost the line here. Okay. The top part we got the same. They just wrote it funny. They wrote the 2xy together and the x in another place. So 2x squared y e to the x squared y plus e to the x squared y. Okay, the partial derivative of f with respect to x at log 2, 1 log 2 would then be, and they again wrote it in backwards from me, 4 log 2 plus 2. Got it. Okay. Now they're doing, sorry, the partial of f with respect to y, and they came out the same thing we did, x cubed e to the x squared y, and then plugging in 1 log 2 here. Okay, they have e to the log 2, which is just equal to. Okay. They didn't do any more with it. Now we get to the slides we just did. Okay, where it says informally the values blah blah blah. We've already done that slide. Now they're ready for example 3. Sorry. Now example 3 you can also find at larsoncalculus.com. Interactive version of this type of an example. So here we have, find the slopes in the x direction and in the y direction of this function, f of x sub y, when that's equal to minus x squared over 2 minus y squared plus 25/8. At the point where x is equal to 1/2, y is equal to 1, and z is equal to 2. Okay. Now, before I do anything on a problem like this, here's something I recommend. Plug it in and make sure the problem makes sense. If you plug in a 1/2 for your x, this will be a minus 1/4 over 2 would be 1/8. So you have a minus 1/8 here, a minus 1 there, so it's minus 1 1/8, plus 25/8. Well, 1 1/8 is 9/8. Yeah, 9/8. And that would be a minus 9/8 plus 25/8. So minus times 25 is 16. 16/8 is 2. Yes, that point is on the curve. Wanted to make sure of that. Okay? So we want the slopes of this curve, this surface actually, in the x direction and in the y direction of the surface of that. That's the surface. So how do we find the slopes in the x direction? Partial with respect to x of xy, and what would that be? Negative x. Perfect. Is that all? Yeah, it is for that, because the partial of this, if you hold that constant, that's 0. Partial of that, with that constant, that's 0. Derivative of constants are 0, and those you treat as constant. This is the only term with an x in it, so that's the only term that counts here, and that would be your minus x, because 2 wipes out the 1/2. Okay? Now there's the partial there, so what would be the slope there? F sub x at 1/2, 1. You don't need the z part in here. What would that be? Negative 1/2. So that slope in the x direction at this point, 1/2, 1, 2. So if 1/2 is 1/2 unit there, 1 is 1 unit here, and 2 is somewhere up here, this is a slight, very slight downward slope. The slope would be negative 1/2. Okay? Now let's do the partial of f with respect to y. And this is also a function of x and y only. And what would that be? Negative 2y. Okay? Now it's also going down. So now again, and let's calculate it. F sub y at 1/2, 1 is equal to negative what? Oh yeah, negative 2, because you put in the 1 there. Negative 2. My hearing is so bad. Okay, now that's much steeper. Same point, 1/2 this way, 1 this way. Okay, so something like this, only now it's this way because it's in the y direction, and that would be a negative 2. Okay, so that's what we got. What did they get? Oh, we'll see on here. Lost it. Yeah, negative 1/2 and negative 2. We got it. Okay. So let's clear this so you can see how they did it. Partial derivative of f with respect to x would be minus x, and with respect to y would be, minus 2y. We did that too. Then plugging in those values 1/2, 1, there you get negative 1/2, and there you get a negative 2. Okay. And that's all they do for that. Now, how are we doing time-wise? 40 minutes left? Is that right? Okay. I wish we had more time to do some of these, but you got the general idea how you do partial derivatives. Now, I also want you to be exposed to, before you move on from here, multiple integration. Boy, there's chain rules for functions of several variables, just like you would expect. There's nothing really any new here. Directional derivatives and gradients, that is a different topic. And let me just say, I don't think we have time. If any of you were civil engineering, y'all are going to have to do that. I didn't ask, Charles, you came in later. What's your major? Second? Mechanical. So you two are mechanical. You might be doing some gradients. I wouldn't be surprised. Goodness, this is a long chapter. Tangent planes, normal lines, wish we had time for it, but we don't. And extreme functions of two variables. Yo! Okay? And then applications of extrema. Lagrange multipliers, we'd never cover that one. But Lagrange is a potential paper topic, meaning, okay, let's go back and hit two things here. First, have you done your student course evaluations? Yes? Yes? All right, excellent. If you haven't, please do those. Number two, I need those papers in. If I get them in today, no loss of points. Anything after today, you start losing points. Okay? But we aren't going to have a chance to do Lagrange multipliers, but Lagrange is a very good paper topic. Finally, that ends chapter 13, and we move on to 14. So let's can this for now. Good deal. Thank you. All right. Discard those and move on to 14, multiple integration. Look at that. 13 has 10 sections. 14 has 8 sections. We're not going to get them all done today, but I wanted you to be exposed to it anyway. Okay? All right. We'll go from current slide. And we'll do iterated integrals and areas in the plane. Actually, let's just go on to 14.2. Nice stuff there, but I want you to be exposed to 14.2 at least. And then we may jump up to triple integrals 14.6. Okay. Double integrals and volume. Use a double integral to represent the volume of a solid region and the property of double integrals. And use properties of double integrals. We'll evaluate double integral as iterated integral, and we'll find the average value of a function over a region. I doubt if we'll get that far. Let's just do double integrals for now. You know that a definite integral over an interval uses a limit process to assign measures to quantities such as area, volume, arc length, mass, and so on. In this section, we'll use a similar process to define a double integral of a function of two variables over a certain region of plane. Consider a continuous function f, such that f of xy is always greater than or equal to 0 for all xy in some region R of the xy plane. Now they're showing this. Let's go out so many units here on x, so many units on y, so many units up on z, and now we have our sort of like an igloo coming down off of that. This will be our volume, the solid region here, connected by, it looks like it could be a quarter of a circle or an ellipse or something here, and coming down, touching those boundaries. Okay? Doesn't matter what it is, but the f of xy is always greater than or equal to 0 for all xy's in the region down here. Not the region out here, that looks like here it'd be going below him. Just of this curve here, whether that's a quarter of a circle or part of an ellipse or whatever it is, in this region here, this xy region here, this thing is always positive, above 0. G is above 0. Okay? The goal is to find the volume of the solid region lying between the surface given by this, the xy plane, and where it ends there. Okay, just in the first octave, you might say. Z is equal to f of xy. Okay? Now, you can begin by superimposing a rectangular grid over the region. Okay, so put a rectangular grid, delta x is this way and delta y is that way. Okay? Now, some of these things will be outside and they won't contribute anything, but we'll take those on the inside. The rectangles lying entirely within R form an inner partition whose norm is called this delta. Okay, defined as the length of the longest diagonal of the nth rectangle. Okay, of the n rectangles. So let's just go up from one of these until you hit here. The longest diagonal of that rectangle is what we're talking about. Okay. Don't sweat it too much. It'll, I think, start making sense a little bit later. Next, choose a point, x of I, y of I, in each rectangle and form the rectangular prism whose height is f of x, y, y, x, I, y, I. Okay? I think those are i's. That's the height of that prism. Okay? Now we took the highest point to be that one. There's the prism, and there's the height of the prism, this f of xi, yi. That's the tallest prism, so you're going to be overshooting the volume a little bit. because the area of that ith rectangle is delta a sub I, fine, it follows that the volume of the ith prism is that area times the maximum height. Now that's going to be the maximum volume of this, because you're choosing the back corner, the highest corner, to be the one you're going from. So you're overshooting a little bit, but not by much. Okay? The volume of the ith prism, the height times the area of the base. You can apply the volume of a solid region by Riemann sums with the volume of all the n prisms that you have, and that would be the summation from I is equal to 1 to n of alpha of x sub I, y sub I, times your delta A. Okay? Which is your area increment. Okay? So here's what you got then. The blue parts are the actual area under that. The red parts are the part you overestimate. Okay? But of course, you've also underestimated any part that didn't have a full rectangle here. These are only parts of the square being covered, so you don't even have any of that. So you're underestimating here, overestimating with the red. So you shouldn't be far off. Okay? You know how Riemann sums go. Approximate the volume of the solid lying between the parabola. The parabola f of xy is equal to 1 minus 1/2 x squared minus 1/2 y squared, and the square region. Sorry. Oh, this is example 1. I said they didn't give us any of this. Okay, let's go to here. Now I'm wanting basically to cut to the chase here and not do it a Riemann sum. Let me just show you how to do the integration. That's what we're trying to integrate. But you see we're integrating twice, once with respect to x and once with respect to y. So approximate the volume of the solid lying between the paraboloid. I know it's going to be two integrals because it's got two variables. 1 minus 1/2 x squared minus 1/2 y squared. The square region given by r given by 0 is less than x less than 1, and 0 is less than y less than 1. Now because I said this for x and this one for y, okay, then you always do the innermost one first, the x, dy. Because if you ignore the y's here, you've got an integral with respect to x. And then once you do that, you can do the integral with respect to y. So you always treat them interior first and then go to the exterior. Okay? So let's do the integration. You're first integrating with respect to x. Ignore the y. Treat it like it's not even there. Okay? Treat it like it's a constant. Okay? So we're going to not throw it away. 0 to 1, this is on y. What's the antiderivative of 1? With respect to x. X minus okay, you got a 1/2, I admit that.
What is it, like 3/2 x cubed?
X cubed over 6. Okay, so that's going to be a total of x cubed over 12. Okay, minus, guess what? You treat that as a constant. 1/2 y squared x. Okay, we're going to evaluate that from 0 to 1. But these are x values. Remember, x equals 0 to x equals 1. And then we're going to have our dy. That dy goes with this integral here we haven't done anything with yet. So we're evaluating this right here between 0 and 1. That's a pretty easy evaluation. I hope you'll agree. You just plug the 1 in there and you get, I'm going to write down the integral from 0 to 1. This is the y integral that we haven't done yet. And this will be 1 minus 1/12, right? Because x equals 1. That would just be a 1/12. Minus, you're not integrating with respect to y, so you're 1/2 of 1 is 1/2 y squared. Okay? Then you still got your dy to go. But now we have a function, well, let's clean this up a little bit. This will be the integral from 0 to 1 of 11/12 minus 1/2 y squared dy. All right. And need to put that in. Now these are the limits on y. Same limits, but they're on y now. So what would this give you? Antiderivative of 11/12 would be antiderivative of a constant would be it would be 11/12 y. It's just a constant, right? Okay. Up the exponent by 1 from 0 to 1, you got it. Okay? Minus, what would that next one be? Integrated antiderivative with respect to y. Wait a minute. I'm sorry. I was listening to what you said, not thinking about it. You were already multiplying the 3 by 2 and got 6. I thought you were giving me the 6 because I looked at it and say, how do we get a 6 down there? That's what we got. So this one is not a 12 but a 6. Whoops. Yeah. Nope. Can't get my eraser to come up. There we go. Well, let's see. Yeah. I think we'll be all right now. So this is 1 minus 1, 6, which will be 5, 6. And that then will be 5, 6y. Okay. Minus 1/2 times what you get here. Antiderivative of 1/2 y squared. Anybody? Y3 over 3. That's when I saw that. I said, how do we get a 12 there before? Okay, and this is evaluated from 0 to 1. So this will be 5, 6. And by the way, I didn't show you, but when you evaluate this one down here at 0, that's all zeros. Okay, so that's why I didn't do anything there. Okay, so you get 5, 6 minus 1, 6, and that gives you 2/3. So that, I think, is the volume. This is example 1. Why in the world is example 1? Oh, I see why. We're in, I didn't turn my pages over to the next section. Okay. They did it by Riemann sums. We didn't. They got 0.672. What do we get? 0.677. We got it exactly. They came pretty close, though, surprisingly. Okay? So, let's keep trucking. Okay. Do y'all want to do the Riemann sums and do your raise like this? Please say no, okay? You could if you had time. We don't. They got 0.672. We got 0.667, okay? Pretty close. The exact volume is 2/3, and that's what we got. Okay. The finer partition, the better estimate you get. For example, with partition of squares of sides length 1/10, the approximation comes out 0.668. We got 2/3. Awfully close there. Okay. Note that by using finer partitions, you obtain better by their approximations. That observation say what would happen if we took a limit. Remember, the del was the longest diameter of that space, and you let that approach 0. So you're going to be how you get the delta A may involve some figuring to get those, because your delta X is getting smaller and smaller, and your delta Y's are getting smaller and smaller, so your delta A is also. This precise meaning for this limit is defined just as we've always done all of our limits, so I'm going to leave on. So the definition of the double integral is the limit as that del, that longest diameter, is approaching 0 of that summation, and that's what gives you the integral. Now, I really don't care for the way they're writing this. They're writing x1, xi, yi as if they're treating them both at once. Really, what you're doing is doing them twice. Well, I guess with the r here, you sort of like you are doing it once. But in reality, you're going to have a double integral. You'll see that definite integral is sometimes referred to as a single integral, what we've always called before a definite integral. Now it's going to be a single integral. Okay, sufficient conditions exist for that. Okay. I don't think that's super all that important. What they're saying here, basically, if you have a really odd-shaped region, then split it into 2 and add the 2 together. You know, if you have some surface over the top here, do it and add it together. Okay? As long as those 2 regions don't overlap. They can't include anything in common. Only the one boundary. That's it. A double integral can be used to find the volume of a solid region that lies between the xy plane and the surface C is equal to Fy. So here's what it is. If F is integrable over a plane region R, and F of xy is always greater than or equal to 0 on those xy values in R, then the volume of the solid region that lies above R, below the graph, is the double integral from R to f of x dA, where dA is usually dx dy. Not always, but quite often, dx dy. So here are some of the properties for double integrals, and these will extend to triple integrals, or any number that you've got. If f and g are continuous over a closed, bounded region, plane region R, and c is a constant, then the double integral of that region is the constant double integral of that region of, here's Daniel, okay, double integral of a constant times a function. Pull the constant on the outside just like you could with any integral. Pull the constant on the outside, and it's the double integral of the function dA. Remember, the dA could be dx dy or some other combination, whatever covers the area. The double integral of a sum or difference of 2 integrable functions, dA, would then be the sum of the 2 double integrals of those functions. Okay? The double integral of a function, dA, if that is greater than or equal to 0, it will be greater than or equal to 0 anytime f is greater than or equal to 0. If f never is negative, the double integral surely can't be negative, because you're adding up the positive heights times some sort of area. And here's sort of the squeeze type theorem. The double integral of f is greater than the double integral of g if f is always greater than or equal to the double integral of g. If f is up here, g is down here, you measure it here, sure, the volume under that g is going to be less than or equal to the volume under f. And number 5, the double integral of f of x dy of a big region is the little regions as long as these are no longer, there's no way they're overlapping anywhere. Then it would be adding the area under this region plus the area under that region, where R is the union of the two non-overlapping subregions. Okay. A lot of blah, blah, blah. How do we evaluate these? Okay, here we got one. Consider the solid region bounded by the plane z is equal to f of xy, and that's equal to 2 minus x minus 2y. So this is a plane that cuts down like this. How you can tell where it forms is that x equals 0, and you have z is equal to a function of y, and that would be 2 minus 2y, and that would be this function here, this line here, 2 minus 2y, z is equal to that would be z is equal to 2 times x minus 1 minus y, so it's going to intersect here at 1, 0, so plug in a 0 for 1, and your z is going to be 2, so 0 is on x, 0 is on y, then this is going to be 2. Then just shut down one, play with the other. This one's going to go have an intersection that when y is equal to 0, x is equal to 0, this one will be 2. I'm sorry, z is equal to 0, and y is equal to 0, x is going to be 2. Over here at 0, 1, 0. So you've got that triangular cross-sectional area. Now, how are you going to do the double integral? This is where it gets a little tricky. Well, no, it really isn't too bad at all. What you do is pick you first what variable you want to be the last thing you integrate. They chose your dx's here. Get a very, very small dx here. Okay? Looks like it's just a single line almost. Tiny little delta x. Okay? Now, at that value, you're somewhere between 0 and 2 on x. That value this value up here is z is equal to 2. Down here, z is equal to 0. So along this line here, this height here is going to be 2 minus x. Okay? Because your y value is 0, so that's going to be 2 minus x. So that's the height here. The base here of that little triangle is going to be the portion here. Your x is going from, your y value here is going from x equals 0 to x equals some value right here. What value is this here? Okay. Well, this line down here is where z is equal to 0. So you have let me write this out because it's hard to explain otherwise. If z is equal to 0, you have 2 is equal to x plus 2y, right? Now, if you solve that for y, then you would be 2 minus x over is equal to 2y, divide both sides by 2, and that's how they get this. The y is equal to 2 minus x over 2. So this is your y value. So the area of this little triangle here will be 1/2 the base times the height. Well, you already had a 1/2 in here. You have another 1/2, so it's 1/4 this times this. Well, this is just this thing squared, 2 minus x times 2 minus x. Okay? So that's your triangular cross-section. And then you sum that from 0 to 2. Okay? So that's going to be your last one. Your first one, so it's the integrating from 0 to 2 on dx, that's what we showed here, this area that we just described here. 1/2 this base times that height. Okay? This is far more detailed than I wanted to go into today. So there it is, 1/2 that base times that height. So it would be 2 minus x squared over 4. And you're integrating that from 0 to 2. Okay? And you reduce everything down to a single integral. Okay? Now that procedure, no matter works no matter how your a of x is obtained. And that's sort of an awkward, convoluted way of doing it, but certainly it works there. But let's see. I wanted to get into double integrals, and they just are slow getting there. So here's, finally, we get to here. Here's another way to write it. Okay? You're first going from 0 to your y value, and your y value was 2 minus x over 2, and then finally 0 to 2. So you're doing the y value first, but you're using the function of x, so that's why you put your dy on the interior, and then you do the integral with respect to x from 0 to 2. So let's do this integration right here. Okay? Actually, they've done it up above, but it's awkward. I need some space to write. Tell you what I'm going to do. I'm going to open another slide. How are we doing? We go to 2:10, so we got 10 minutes left. All right, let's open this slide. Okay. What was that integral we had? The double integral, and I'll get my pen back. All right. The double integral, the last integral, the outside one is going to be 0 to 2 on x. So there's our dx. Okay? The inner integral is going to be your dy, and the dy is going from 0 to, remember we calculated that be 2 minus x over 2. That's your upper limit on y. Okay? And then we're doing that whole surface, which is 2 minus x minus 2y. That's what they gave us. All right. Now, again, we're doing the inner integration first. Sort of forget about the dx and this outer integral. We're just doing that integral. And in doing with respect to y, meaning we're treating the x's and any other thing like a constant. Only integrating with respect to y. Okay? So I'll write down the integral from 0 to 2 and the dx and leave that alone. Okay? Now what's the antiderivative of 2 with respect to y? It's pretty easy. Anybody? Antiderivative of 2 dy. 2y. Perfect. Okay? Minus, what's the antiderivative of x with respect to y? xy. Okay? And then the antiderivative of 2y with respect to y. It's even easier. y squared, okay? Now, we're going to evaluate that from y equals 0 to y is equal to 2 minus x over 2. Now, I'll put the y's in there so you'll remember that's what we're substituting. We're not substituting anything for x. X will stay right there, just like the 2 will stay right there, okay? So let's simplify this a little bit. Still going from 0 to 2. We're not ready to do that last integration yet, but let's plug in the values. So 2 times, and the first y up here is 2 minus x over 2, right? Minus x times 2 minus x over 2. Minus 2 minus x over 2 squared. Right? Then we could do the same thing with respect to 0, but that would give you a 0, a 0, and a 0. So they're not going to contribute anything. So let's clean those up a little bit. 0 to 2 stays, the dx stays. Okay? Now, the x's stay, but let's evaluate everything else. Well, this 2 and that 2 disappear. You know, they divide away. They multiply to be 1. Whatever you want to say. And this will be a 2 minus x minus 2x plus x squared over 2 minus 4 minus 4x plus x squared over 4. Okay, that's pretty nasty looking, so let's see if we can clean it up some. 0 to 2. Let's just work this out. Let's get everything over 4. So this would be 8 minus 4x minus 4x plus 2x squared minus 4 minus 4x plus x squared over 4. Okay. Wow, is there anything we can do with this? Well, there is a 8 and a minus 4. That was going to be 4. There's a minus 4x, another minus 4x, another, let's see, whoops, that one's supposed to be a plus 4x. And that was supposed to be a minus x squared. So let's go back and do, well, we'll get to that one, okay, because I forgot about my minus in front. And I forgot this one too. There's a minus there too. Minus a minus. No, I got that one. Sorry, I did that one. I didn't do that one. Okay. Okay. So I think we have 4 minus 4x minus x squared over 4. That's what we're integrating, I think. Okay, I'm pulling the 1/4 out. It'd be 4 minus 4x minus x squared dx. Now let me see. I want to make sure I haven't made. Oh, I don't think they're doing this in the book anyway, are they? Let's see if they do. All shame on them, they didn't. That's a different problem. And frankly, I don't even know if they give you an answer for this one. So rather than carry it any further, from there on it's just a single integral. Go with it. They don't give an answer, so let's not spend any more time on it. Okay, so let's get out of this and back to where we were. And that was here. All right, that was the integral we were just doing, and they didn't give an answer for it anyway. To understand this new procedure, well, actually, now that I think about it, they did. We'd already gotten that answer. I've already erased it now. To understand this procedure better, it helps to imagine the integration as two sweeping motions. For the inner integration, the vertical line sweeps out the area of cross-section. Okay, so first you're integrating from this base out here. So you're integrating the cross-sectional area, and then you take the next integration and integrate that all the way down the other axis, and that gives you your full volume. Okay? So, here's Fubini's theorem. And if you haven't done a paper topic yet, time again for the advertisement. First, do student course evaluation. Next, get your papers in today, not to lose any points. Anytime after today, you start losing points. Okay? Now, Fubini's theorem. F be continuous on the plane region R. Okay? If R is defined x between A and B, but y is between the G1 of x and the G2 of x, okay, where those are continuous functions on AB, then the double integral over that region of alpha of x dx, which is defined everywhere here, always do the inner one that do your dy first, because that's given in terms of functions of x. Once you get that done, then what's inside here will all be functions of x, and x is going from actual numerical limits. Okay? Now, if you define it the other way, that y is between numerical limits c and d, and x is between h1 and h2, do the inner one being the dx, and go between h1 and h2, the lesser one to the higher one, and they are continuous on CD, and then finally do your dy next. So whichever one you have the outside information on, do that the last one, and one that depends on the other, do that as the interior one. Okay? Fubini's theorem. Finally, we get to do one. All right. This one is just between rectangular limits. I forgot, I have to go back to black again. But we can do that. Okay, so let's do it first. Be easy. So this will be the integral. And it doesn't matter which order, because you know the values for all of them. So we know both of them are going from 0 to 1. We already, didn't we do this one? Does that come out? Yeah, we've done it. That came out 2/3. Remember? I already did that one for you. So let's move on to example 3. We already did all this. Okay, this is just redoing what we had already done. So let's do example 3. Find the volume of a solid bounded by the paraboloid z is equal to 4 minus x squared minus 2y squared. Okay. Wait a minute. Have we just gone over? Yeah. Sorry. Not going to be able to do example 3. I wish it had been more focused on double integrals. But you see what you do. You integrate the whatever the inner thing is with respect to y. This you treat as a constant, so that would just be minus 1/2 x squared y. This would just be a minus, that would just be a y, and this would be a minus y squared. No, I mean minus y cubed over 6. We had already done that before. I'm going to do this one, but you do the same thing. Whatever your limits are, and if it matters, that one doesn't matter what. If you only know one of the limits in terms of the other, get those on the inside, and then the ones you know the full outer limits for, do that last. That's a quick and dirty on multiple integration. Sorry about that. It's really pretty fun to do most of the time. And you can do a lot more complicated problems with a lot less angst than you could trying to do it with single integrals, like they tried to at first. I said, let's get on past that. All right, that's it. Please do your student course evaluations. Get your other papers into. Oh, I meant to return papers to you too. Has anyone not turned in test 1 or 2? Huh? Okay.
There's also my paper from.
What's that?
That's also my mini article paper too.
Okay. Okay, where's one for this one?
I might have to email you that later.
Okay, well, okay. Well, just get it to me. Okay, and this is your test 2, and you're doing test 2 also. Have you done test 1?
It is test 1.
Huh?
It is test 1.
When did you turn it in? I don't recall having a grade for you for test 1. Let me see. No, I never did unless you turned it in recently. Well, that's something I can't worry about now. Okay, let me get these papers back to you. Okay. Okay, this morning, every time I look for Cal 1, I got in Cal 2. Now when I look for Cal 2, I'm in Cal 1. Okay. Cal 3, I'm in Cal 1. Okay. Nope, still in Cal 2. Okay, now I'm in Cal 3. Few people had turned in papers. Okay, here we go. Now it's your test 1, which was a Cal 2 test 2. Here's Vince. Charles is from Alice. That's still here. Or has to go home because air conditioning died, the cleaning guy. And Jordan's not here. Jordan didn't happen to send in any. He may have already turned in everything. Okay. Second test. Go like that. Vince. Charles. Brian. Well, you just turned yours. You just turned yours. Second test. All right. Finally. Sort of. Get me there. Here we go. Here's your last test, the final, whatever you want to call it. It says test 2 here. It's actually your test 3. And this is mostly that last chapter we did, which was chapter 12. No. Sorry for the pause. Was it 12? I think Gordon, did he pick up one? Where is it? This is, I ran off 6 copies. 1, 2, 3, 4, 5. I asked her to run off 6. Oh, Clark already picked up his. So that's 7. I have one in here. Maybe I'll do. You say you're going to get one for him? Sorry, it is a little print. Thank you. Okay. Good deal. Enjoyed having y'all in class. Most of you for the multiple times. I think maybe first time for a couple of you. But please do the student course evaluations and give me. Oh, let's talk about schedule toward the end. Okay. Are any of you graduating this term? Any? None. Oh, that's interesting. Okay. Whew. That relieves some pressure. Is Jordan. Is he? Okay, and you've already graduated, or? Yeah, okay. So Jordan's going to have to give me his final exam back by Thursday. The rest of you have until next Monday. But if you can get it back to me sooner, get it back to me sooner. But I have to have it by Monday because your grades are due in noon Wednesday. Jordan's is due in noon Friday. So I have to have his by Thursday, yours by Monday. And if you haven't got me your papers, get them to me today, or else you'll be losing points after today.
Are you going to be here Wednesday?
Oh yeah, let me give you that schedule too. I'm here. I've got one more class coming up at what time is it now? 2:10 or something like that. I have a class starting at 2:30. It goes to 3:45. So I'm here from 3:45 till 6 today. Tomorrow, for some reason, even though the classes don't start till 8:30, they start at finals at 8. So I've got a final tomorrow morning from 8 to 10, 8 to 9:50 technically, but I'll probably be in there until 10. That'll be down the hall in 205. Then from 10 to 1:15, I'll be in my office at 265. However, my second mini-term class still has a class tomorrow, so I'll be in class from 1:15 until probably around 3:45, because all we have to do is a lab and a test. So the lab will probably take about 2 hours, the test will probably 30 minutes. So I'm guessing 1:15 till 3:45, okay? Then from 3:45 until 6, I'll be down in my office to 265. Then on Wednesday, I have no classes, no formal finals, but I'll be here from 8 until 4 o'clock, down in 265. But at 4 o'clock, I have to leave to go to the Birmingham East Campus, and my physics class there will be turning in their work from 4:30 to 6:30. So if that's more convenient to you, I'll be on the Birmingham East Campus. That's the nursing building down on the first floor, room 103. When you go in, that triangle there, hang a left back by the office to go past the restroom, first door on the left. So that's from 4:30 to 6:30 on Wednesday. Then Thursday, I'll be in my office from 8 till 1. At 1 o'clock, I'll be administering the final to my second mini-term class here. That won't take them more than 30 minutes, I don't think, 15 to 30 minutes, a pretty short and easy final. So that's going to be 1:15 to 1:30, 2 o'clock, something in there. Then I'll be back in my office after that until 6. And then on Friday, I'll be on the Birmingham West Campus from 8 to 12. Okay? Then Monday, I'll be on this campus in my office, 265, from 8 to 6. And then Tuesday, I'll be here 8 to 6. Wednesday, I'll be submitting your grades from 8 to 12. And I may have them in before that. But that's what that's left for. And then after that, I'll be here till 6 o'clock Wednesday, and I think Thursday and Friday too. Oh, well, Friday only 4 hours. Well, Friday is the graduation. Well, no, actually, now that I put it on. Thursday, I will not be here because we've got a nephew getting his master's at LSU, and I would normally be here, except we have been designated to drive the grandparents down to the graduation at LSU, so I will be gone Thursday and Friday. So I'll miss your Jordan's graduation. Sorry about that, but because I'll be at LSU at theirs. So anyway, good deal. And then I think we even have a duty there or two the next week. Not many, no more than one. But anyway, that'll be it for the term. So please get the stuff into me as soon as you can. And do the student course evaluation. Good deal. Excellent. Good deal.